I'm Fiona Solomon. I'm the CEO of ASI, and my pleasure to be introducing Chris Bayliss, Director of Standards here at ASI, who's going to be giving us a nice rounded overview of the 1.5 degree pathway for the aluminium sector and rolling that into discussions coming from you, our audience. So do share those questions starting from right now, and I'm going to hand over to Chris to kick us off. Thanks, Chris.
Thanks very much, Fiona. Thanks everyone in advance for your questions. Yeah, as Fiona said, keep them coming as we go along. I'll talk today a little bit about the kind of the shape of the industry today and its emissions impact, and then this 1.5 pathway to mid-century as defined by the International Aluminium Institute, and maybe some of the drivers for change that need to happen to get the sector there. But I also hope that maybe through the questions we can start talking about what that means for individual entities as they certify with against ASI's performance standard as well. Some of the numbers I hope are well known, but if not, maybe we can talk a bit about those. Today, the aluminium sector as a whole, all the way through from bauxite mining right the way through to semis production, so the production of semi-fabricated products, including a recycling loop, including the energy needed to remelt scrap, and including all of the other inputs to the aluminium production process. So that's sodium hydroxide for alumina refining, alloying elements, carbon in the anodes, the actual carbon that flows through, plus the emissions embodied in things like energy carriers, so in the coal that's burned for coal-fired power. All of those inputs, all of those material and energetic inputs, they all have a carbon footprint. And for the industry as a whole globally today, that amounts to around 1.1 billion tons of carbon dioxide equivalent, 1.1 gigatons. That's about 4% of global CO2 emissions, around 2% of global greenhouse gas emissions, anthropogenic greenhouse gas emissions as a whole. So the aluminium sector is a significant emitter. It's responsible for a significant part of those emissions. Second, it's in the same kind of order of magnitude as global shipping. It's not far off steel, really. You know, steel's often seen as this big, hard to abate sector. It's not orders of magnitude different from aluminium, even as its production is orders of magnitude higher. It's really only three or four times higher than the aluminium sector as a whole. So the industry today, significant emitter all the way along the value chain. Also a significant a significant driver for decarbonisation elsewhere in the chain. So the use of aluminium to lightweight vehicles or to build green buildings, have energy efficient, energy saving, window frames, in packaging, lightweight packaging, protective packaging that protects foodstuffs and medicines. They're all beneficial impacts on the downstream and lend themselves to decarbonisation in other parts of the system. We'll talk a bit about that later on. But that comes with a cost. It comes with the CO2 emissions impact of that 1.1 billion tonnes today. Based on International Energy Agency modelling that's then been taken by the International Aluminium Institute and applied to the aluminium sector, that 1.1 billion tonnes of emissions under a 1.5 degree scenario will need to come down mid-century by 2050 to around 50 million tonnes of CO2 equivalent. So 1,100 million tonnes today to 50 million tonnes mid-century. So that's a 95+% reduction of the emissions of the industry as a whole in the next 30 years. Even as the sector is predicted, if not to grow, then at least to maintain its production volumes in order to meet these demands of other decarbonising sectors, as the automotive industry wants to lightweight, increase electric vehicle production, as architects and specifiers want to build green buildings, as packaging moves towards even lighter weight, lower gauge materials. That pull for, as electrification increases, that pull for aluminium through the system is set to be a steady state or maybe even increase. So increase production while decreasing emissions by 95%. I can't overstate enough, I think, the challenge for our industry or the aluminium industry to achieve that. And it's not just the aluminium industry, all other sectors will need to have similar pathways in order to achieve a 1.5 degree mid-century endpoint. So there's some challenges around that, one of which is that everyone else is going to want access to low carbon energy sources as we move towards mid-century. So we are not alone in needing to decarbonize our energy, or the aluminium sector is not alone in decarbonizing its energy profile. Others will want access to that energy too. So let's take a look actually at what those decarbonisation pathways might look like. But before that, maybe is to say that the ASI, the Standards Committee within ASI, made a commitment to a 1.5 degree pathway for the aluminium sector some years ago. And that commitment has recently been embodied, articulated in the version 3 performance standard, which was released a couple of months ago now. It's embedded in principle 5, specifically criteria 5.3, this need for 1.5 degree pathway, not just for the sector as a whole, but for individual entities to plot their pathways in order to achieve that sectoral change. And there's some interesting bits in that, and there's also some conflict in that as well, because that 1.5 degree pathway for the sector as a whole is a systems change. That IEA approach is the whole of global economy. You know, it's this idea that the whole global economy will decarbonize, and different sectors will play their part to provide material to decarbonize, battery, metals, you know, increased biogenic material inputs, increased aluminium, while the system as a whole decarbonizes. But we need to look at what individual players do within that. And we may see some more able to reduce and some less able to reduce in order to meet that 1.5 degree target. And specifically here, the interesting thing, I think, is around the primary industry, but increasingly around scrap and the flow of scrap material as well. Because as we recycle more in the future, of course, that lends itself to lower emissions, in theory, but the energy required to remelt that scrap increases over time. And so entities that are involved in recycling may find their what's called scope 1 and 2 emissions increase as they put more energy in to melt the scrap that is required to decarbonize the system as a whole. I can say in general across the sector as a whole, no one gets away with not reducing significantly. So the primary sector, the primary industry, I think is probably the best articulated in the International Aluminium Institute's 1.5 degree pathway. It says that all electricity related emissions, and they make up around 70% of aluminium sector emissions today, all those electricity emissions, predominantly in the smelting process, the electrolytic process, they reach zero by mid-century through a number of routes, through connections to decarbonised grid, investments in renewables, more localized grids, these kind of things, battery storage, etc. So the primary aluminium sector, that kind of pathway is relatively clear. Over and above that, there's then needs to be investment in new novel technologies to remove carbon from the process. You may have heard anode is one way to get rid of that CO2 from the electrolytic process, carbon capture, utilization and storage another. And then some of the heat thermal related processes, casting, remelting, alumina refining, they will require decarbonizing as well. So you'll need things like green hydrogen, again, carbon capture, utilization and storage, some kind of novel technologies like in alumina refining, kind of reuse of steam. Those kinds of emissions reductions will need to be of the order of magnitude of around 90% for the primary sector. So that means not just technology change in one place, it means technology change and then dispersal across, or implementation across the whole of the sector. But even with that, sorry.
Oh, no, sorry, you're in a role. I was going to say we had a question, which I thought just flows in from where we were. We talked about that 50 million tonnes budget by 2050. Where does that come from? Because we hear about net zero, and so what does that mean?
So that 50 million tonnes, as I said, the electricity is zero. So you can say that there is no electricity related emission in that 50 million tonnes. That's the electricity that currently goes into electrolysis. But the IEA and III are kind of neutral on what technologies are deployed, but one might expect that current thermal processes, casting, remelting, anode production, although you might see anodes get out of the system, they will increasingly be electrified. So you actually see an increase in electricity demand for the aluminium sector to electrify thermal processes. And that electricity needs to be zero. So you can say that 50 million tons mid-century, the electricity component, and today that's around, I think it's about 750 million tons is gone. So that's a big thing, right? Currently, the aluminium sector, primary aluminium, 60%, 65% of aluminium primary production is coal-fired. So that would all need to be grid connected or renewable connected in some way. So that 50 million ton share, that's the kind of that's the budget. Where it goes, that's the big question. So who gets the allocation of that is the important piece. And if you look at the IAI's numbers, that is actually allocated between the primary and the downstream. And essentially the primary sector with all of these technology pieces would need to then reduce down its direct emissions by around 90%. But the semis production and the recycling folks, as more scrap flows through the system, will still need to reduce their emission profile by something like 70–80% by mid-century. So that 50 million tons is pretty, I can't remember the exact numbers, they're certainly available, and maybe I'll send afterwards the spreadsheet that shows this. I think it's split about 50–50 between primary production, then downstream and recycling. Whereas today, of that 1.1 billion tons, about 1.0 billion tons is in primary production. The rest is all in other processes. So you can see that the share of downstream and recycling grows from today around 5%, something like that, to 50% by mid-century. So there's actually a growth in the share, but in absolute terms, everyone reduces, and everyone needs to reduce in order to meet this 1.5 degree pathway, which is built, as I said, top down. It's from that IEA's whole of systems approach. 1.5 degree, what does that mean? It's net zero. You'll sometimes hear about this net zero. If the aluminium sector emits 50 million tons mid-century, there needs to be 50 million tons removed from the atmosphere in order for net zero to kind of occur. And that's why maybe I'll kind of labor this point a little bit. Net zero kind of only makes sense at the total global economy-wide scale. Net zero is where we, as an anthropogenic system, need to be mid-century. But the aluminium sector getting to net zero is kind of, then that's less efficient in the system. So actually, you'll find removal of our 50 million tons, and the IEA say that's predominantly coming from the power sector elsewhere in the system. So yes, scrap today, scrap is provides around a third of the global demand, semis demand. So there's 100 million tons, give or take, of semis demand globally today. So if you take that 1.1 billion tons as a whole, cradle to gate, and divide that by that 100 million tons, you're looking at a global average, and this is kind of, it's not so useful because the semis are lots of different forms, but in general, the semis production is 11 tons per ton, 11 tons of CO2 per ton of aluminium semis production. And you may know the number of 16 tons per ton, that's the global average for primary. So as the primary flows through the system to semis, it's watered down by the 0 tons of scrap, the 0 tons that comes with the scrap coming in. So 65 million tons of primary produced at around 16 million tons on average, with 35 or so million tons of scrap coming into the system, makes 100 million tons of semis production. And under the 1.5 degree scenario for the sector as a whole, that share of demand being met by scrap is set to increase, but only to around 50%. So by mid-century, the modeling shows that only 50% of demand is met through scrap-related sources. The other 50% continues to be met through primary production. And the reason for that is availability of scrap, availability of quality scrap, but just in general availability of scrap. a large proportion of aluminium products are long lifetime products. We see the very visible, let's say, canned and packaging coming through the system very quickly, but the vast majority of aluminium going into the system actually stays in use for a long time. And so unless you reduce those product lifetimes or significantly increase collection rates, you don't get it back for a long time yet. Now, increasing collection rates at end of life is a route that needs to happen. So the improved collection of end of life scrap to close to 100% would today deliver an additional 8 million tons of metal, which would be 8 million tons of primary. We'd require less today if you assume that the end of life scrap is of a good enough quality. So the 1.5 degree scenario says not only do we need to get that, not only is that scrap availability going to increase, but not so that it can meet 100% of demand. We as a society need to improve collection rates to above 90–95% and get that end of life scrap back into the system. A couple of issues with that. One is that the scrap is regionally dispersed, and not only is it regionally, it's not available to all in the same way that low carbon energy is not accessible to everyone on an average scale. Not just that, it's in variable qualities. So in North America, in Europe, we have highly mixed scrap. It's a function of our of the fact that metal's been going through the system for a long while, the fact that it goes into automotive routes that then get shredded and mixed at end of life. Whereas in China, there's much higher quality scrap coming out of buildings because building scrap tends to be higher quality. The building lifetimes in China are much shorter and collection rates for building are very good. So the Chinese access to scrap, high quality scrap, and a shorter lifetime is actually more favorable for, let's say, China than it is for the rest of the world. If you assume that that Chinese metal, that Chinese scrap stays in China. Today, though, while 30% or a third of demand is met through recycled sources, only just over half of that 30% comes from post-consumer scrap. A significant amount, something like today, let me see what the numbers are. Today, so around, let's say 15 million tons of that 35 million tons of scrap that is recycled. 15 million tons is pre-consumer scrap. It's scrap that has never actually been in a product. It's produced during the production of fabricated goods or semi-fabricated goods. And so it's an internal scrap loop. And collection rates for that scrap are very high. You know, it stays within the industrial system. Its value is well understood. It tends to be well sorted because it's controlled by industrial players. Not necessarily, we could talk a bit about that in the questions, but in theory, well sorted and high quality. And so the opportunity for closed loops in that pre-consumer loop are high. But collection rates are very high. So we've got to look at these different drivers, really. The post-consumer side of things, highly dispersed material for packaging, let's say, less dispersed for buildings, poorer quality for automotive where it's being shredded, even though high quality alloys are going into electric vehicles in body sheet and extrusions. The fact that they're going into complex vehicles that are potentially shredded at end of life brings down the quality of that scrap. At the end of life, there are a couple of drivers. One, you want to get that material back. So you want to improve collection rates, but you also want to improve quality, keep the quality. So there's a real role for designers, design for recycling or design for disassembly, taking into account the end of life at the moment that you design and build your product. And that is embodied in our standard. We actually, in the principle for material stewardship, place the onus on, in particular, industrial users, I would say, to design products that enable this scrap to come back at end of life efficiently with high quality. And so there's a real role to be played. It's not just the primary industry decarbonizing its electricity or the downstream sector electrifying its processes and remelting the scrap. There's also a heavy, I'd say, burden on industrial users and the users of aluminium to design to get that material back at end of life. So that's embodied in our material stewardship principles and criteria, but it's also embodied in our greenhouse gas criteria as well, 5.3, where we ask all entities to have in place 1.5 degree pathways for the future. And so those 1.5 degree pathways for the downstream folks, or for the industrial users, will include the role that they play in decarbonising the products or getting that product back at end of life, but also in their procurement, where they get their material from, demanding lower carbon aluminium. So that's the post-consumer. The pre-consumer loop is a different driver. It's not about collection rates or really about quality, although there's some work to do on quality. Because we have high collection rates in pre-consumer and the quality tends to be maintained in these closed loops. There, in the pre-consumer loop, the driver is reducing the generation of pre-consumer scrap. Access to pre-consumer scrap is useful for entities to decarbonize, but the generation of that scrap could be seen as an inefficiency in the system. It never even gets into a product. Of the 100 million tons of semis produced today, let's see how much goes into use. About 80 million tons go into a final product. So you've got 20 million tons that goes around the system, 50 million tons that goes around the system, never actually leaves in a product. And there are technological barriers to that to some extent, but the 1.5 degree scenario in the IEA work actually assumes it makes some claims that pre-consumer scrap is removed from the system. The generation of pre-consumer scrap is removed because that inefficiency in the system, that constant remelting of pre-consumer scrap, is an emitter of CO2. CO2. So again, that's embodied in our performance standard, where we talk about drivers for both collection at end of life, but we also talk about the criteria also demands that where possible, entities minimize the generation of pre-consumer scrap. And this is interesting because in the future, as companies start to build their own slopes and start to build targets, especially those in the downstream, they will have procurement targets as well. They will try and decarbonize their system by procuring lower carbon aluminium. On the one hand, lower carbon primary aluminium, but also increased flows of scrap. And if pre-consumer scrap is high quality, relatively well sorted, and comes with a greenhouse gas impact of 0, that is one route to drive decarbonisation. But in the future, if that pre-consumer scrap loop is minimized, then that is not available. And then all that's available is the end of life scrap. So that puts even more pressure, I think, on the primary sector to decarbonise further. Today, I talked before, the primary industry, the primary sector, that's bauxite all the way through to electrolytic aluminium or cast house, primary cast house, is 16 tons per ton of aluminium on average globally. The highest emitters probably in the 20 to 25 tons of CO2 range. The very lowest emitters, sub 4, you'll hear about 4 tons per ton as low carbon. It's, let's say, 3 to 4 tons is the very lowest you can get today. Really, that's near 0 emissions from electrolytic energy. It's the upstream emissions from alumina refining, from anode production, and then from anode consumption during the electrolytic process. The very lowest is 3 to 4 tons today. But under that 1.5 degree scenario, the primary sector as a whole, on average, would be emitting 0.5 tons per ton of primary by mid-century. That's not the lowest, that's not the highest, that's the average across the whole of the primary sector. So even the 3 or 4 tonners today, and it's not a significant amount, the 4.0 aluminium that's being produced in the world today, I think probably 10-15%, if actually for these numbers, they are available, and we can maybe share some of these data sets afterwards, including CRU, with whom we have an MOU working on some of this emissions data. Those 4.0 tonners, the lowest emitters today, will still need to reduce their emissions by around 75% by mid-century. They tend not to have any electricity related emissions or very low electricity related emissions. So they're at that 0 electricity piece. And that shows that 75% reduction from 3 or 4 tons down to 0.5 is all in their scope 3 emissions, so what they purchase in, and in the scope 1 emissions, direct emissions from the process. So that's things like the use of the inert anode in the electrolytic process, or carbon capture, utilization and storage to capture those emissions during electrolysis, but also decarbonising refining upstream. I don't know if I'm getting across this the scale of this, but that's 65 million tons of global primary production, all of which will need to move at least 75% in absolute terms by mid-century. That's the kind of the big scale. Then, of course, the question is, when does that happen? When does the investment happen to drive that change? And that's a bit embodied in our 5.2 criterion, which talks about smelter thresholds. So you can see there is a slope for the highest emitters to reduce by 2030. And the assumption is that the lower emitters will probably not reduce significantly until after that stage. But that's the big question now, is not just what the end point is and the share between everyone, it's on the specific slopes for individual entities. And that's some of the work that we've been doing with Centre for Climate Aligned Finance, and we hope with science-based targets as part of that group, in order to define specific entity pathways to mid-century as well. As I've talked a lot, so I don't know if there's questions come in. I don't see any, which is surprising, considering we have 60 odd attendees. So maybe I'll stop there and ask for questions, or Fiona, if you have.
Yeah, I've got some couple, but I do encourage everyone to put their questions through. Now's your chance. But yeah, you talked obviously about that kind of close interaction between climate goals, circularity, which are two of our sustainability priorities. We also have human rights, nature positive is our other two, and these are so interconnected. Did you want to talk a little bit about that?
Yeah, so absolutely. So so let's look at that today. Is that 65% of aluminium production, let's say, is about coal-fired, and further 15% or so gas-fired, and we'll see some carbon capture, utilization, and storage, I think, in some of that, but we'll also see increasing grid connection to renewables grids. Well, what do those renewable grids look like? Well, increasingly, they will need things like lots of land, lots of water. They will need significant buy-in from local communities to enable wind farms, solar parks, potentially hydropower, but maybe not so much. And as that decarbonisation happens in grids, specifically in the electricity area, we potentially see conflicts, with local communities, with indigenous peoples, as the beneficiaries of that decarbonisation, i.e. those who are consuming that material. And if you look at the carbon or the material flow, you can see who in the world is consuming and getting the benefit from the aluminium in use, and which parts of the world are not, and then compare that with where it's being produced and where that decarbonisation might happen. They don't always align. So that decarbonisation approach brings with it human rights risks and other risks, water risks, biodiversity risks as well. And that's why in the standard, and as we further develop the standard and guidance, we have to look at that interconnectedness. Increasingly, we talk about area of influence. We've actually included in the guidance now, under area of influence, also the energetic component. So if let's say you're grid connected and it's a decarbonising grid, you're going to have to take into account the impact of that decarbonising grid on local communities, on indigenous communities, on water, on biodiversity. That's part of your responsibility as a consumer of that electricity, or a transformer of that electricity, for the benefits of others. Again, nature positive part of that scope as well. Increasingly in the future, it's going to be a transition. It's an energy transition, essentially, from hydrocarbons towards materials. We're going to need more materials, not just aluminium, but battery materials and others. And they bring with them significant risk, mine-related risks, land, water, etc. So we need to be ready for that and not be myopic in terms of it's all about GHGs. Yes, that's a significant part of the agenda, but it brings other risks elsewhere. And so that's why I think within the ASI standards, this broad ESG focus that isn't just on single issue is a critical piece to bring in, and also to communicate to those who are, I could take for instance the financial sector, who will need to lend the trillions of dollars required to decarbonize aluminium and other sectors. to give them the tools to manage those risks, because they don't have them. They're not experts in the aluminium sector or some of these other sectors. And if they're very focused on decarbonisation, we can add value by bringing this risk management perspective of ASI. And actually, that's some of the work we're doing, is looking at how we can tie ASI certification potentially to some of these financial tools that are out there.
Great.
Yeah.
So we've had a few interesting questions come in. We could probably just go through them in order. The first one's almost an allocation kind of question. So Mr. Zhong has asked about under the COC standard, the chain of custody standard, where you've got ASI and non-ASI aluminium being produced. Essentially, greenhouse gas emissions may or may not be different depending on those raw materials, but there's this broader allocation question, I think, which potentially ties into some of the scrap stuff too.
Yeah.
Did you want to talk about this question about different carbon footprint, how that's assured, what sort of traceability and kind of data downstream users are looking for example?
Sure thing. Well, first one is to say, in the chain of custody standard, we've introduced in the last round under section 9.3 with COC documentation, this voluntary reporting of carbon footprint data with COC documentation, which is it's a small step, but it's a step towards this idea that end users and others in the chain increasingly need to, not just want to, but needs to understand their what are called scope 3 emissions upstream of them. And often the question is, how do I get hold of that data? It's relatively easy, I guess, for my tier 1 supplier to supply their emissions data to me, but what about before them? And so in this chain of custody document, we asked voluntarily for shippers of COC material to actually give a carbon footprint number with a methodology attached to it, so that as it moves along the chain, essentially you're adding scope 1s and 2s and other scope 3s and accruing that, that information to the COC document as it moves through the chain. So that's one way of doing it. I think others are looking at more at a less kind of mass balance approach, and actually looking at specific traceability of greenhouse gas and other data along the value chain as well. So on the one hand, there is this flow of information. I think people should be aware, actually, there's a WBCSD project at the moment, which is looking at, it's not looking at how you calculate the greenhouse gas emissions, it's how that greenhouse gas data is passed along the chain. So it's very interesting. It's one way of doing it. Another is to use kind of proxy data for scope 3s and then applying that generic data to your product. But then the question comes is, what do you allocate to those different products? Because there is, within a cast house, you have a range of products within your portfolio. And there's a range of ways that you can allocate the emissions from your production process. So let's say the furnace emissions, the scope 1s, plus the scope 3s in the material that came in. You can allocate that based on mass, or you could, the mass of output products, or you could allocate it based on the value of those products. So the allocation is in some ways up to you. But then there's also the question of what is embodied in the emissions that came into that cast house in the first place. And here we come to this recycling question, where there are two methods under ISO, both of which are referenced in our standard, and both of which are valid under ISO. To allocate the emissions in scrap. That's a big discussion going on, I think, in the aluminium sector and more broadly as well in the world today, is how does one allocate those? And maybe my job today is to communicate the complexity of that and to talk about the fact that that is a discussion that is ongoing as well. But to say that we, I think, are in an interesting position in that we, under COC, chain of custody, we do differentiate between pre-consumer and post-consumer scrap for its eligibility. So there are mechanisms within ASI to actually look at those two routes separately, even as it can be quite difficult to do that in practice. When you get a bale of scrap together, often pre-consumer and post-consumer is mixed, but at least heuristically, theoretically, we have those loops kind of differently defined under chain of custody, and we do treat them differently under chain of custody as well. And I think you're going to see some work being done by others, at least on the transparency of that, being transparent about what is pre-consumer and what is post-consumer in your system, And we've actually asked for that in 9.3 as well under chain of custody, is if you can voluntarily include your recycled content, and also you can voluntarily split out that information between what's a pre-consumer and a post-consumer flow. Remember, like I said, they're two different things in terms of the drivers of dematerialization and decarbonisation. Pre-consumer, reduce the generation. Post-consumer, increase the collection and quality.
Great. So the next question's from Svetlana about specific trajectories for individual smelters. So as you've talked about and can talk about a bit more, we've got new criteria in the greenhouse gas section, those kind of pathways for 1.5 degrees. There's a methodological piece that's underway with the Centre for Climate Aligned Finance working group. Timing's difficult, but maybe just talk a little bit more about the work that's underway and the bigger picture that you've clearly described, which is we know the slope is steep to get to mid-century.
Maybe we'll talk on practicalities though. Has anyone tried to employ some GHG specialists recently? Everyone wants that. Everyone wants that information because all sectors are going through this, not just the aluminium sector. And so it's very challenging at the moment. I spoke to someone yesterday who was saying they were speaking with consultants who were booked up until post 2024 because everyone wanted this knowledge. So that knowledge capital at the moment is quite limited. And I'll talk about specifically our approach, which was we were looking for science-based targets potentially to revise their sectoral decarbonisation approach, their SDA for aluminium. And actually, we've found that they are overwhelmed. They're at capacity. So it was not possible to go through that SBT route. And that's why we are looking to others, this climate aligned finance group, to begin to articulate these methods and to use the capabilities where it's possible. So that's the first thing, is to maybe manage expectations, including my own, because I was hoping by the end of this year we would have a method, but I can probably tell you now that's not going to happen. Having said that, for primary, I would say, well, we'll see how it goes. I think next year is likely to see something from certainly Climate Aligned Finance want to do something in first or second quarter next year. But for the primary sector, we don't need to wait. For those who are high emitting, the coal-fired smelters, those who are above the ASI's threshold under the version 3 of 11 tonnes per tonne, scope 1, 2 and 3, actually the pathway is quite clear because we've defined it in 5.2, which is to say if you are above 11 today, by 2030, you need to be at 11 or below. So for the really high emitters, or for the higher emitters, the coal fire, that's scope 1, 2, 3 upstream, you need to be on that 11 tonnes by 2030. So that's quite clear already. That's a slope that is clear for the high emitters, and that's 65% of global production. For the very lowest emitters, the 4.0, like I was saying, the electricity for them through historical legacy for some, for others moving towards invested in decarbonised electricity, but relatively few. For those 4.0, actually, they are going to need novel technologies to come through in the system. So you're not likely to see much change to 2030, I would say, in those. You'll see an anode start to be deployed, CCUS in pilot facilities, etc. You start to see that come down a little bit, but not significantly. So for the high emitters, 65% of production, and for the low emitters, actually 2030 is relatively clear. The ones in the middle, that's the bit where it's a bit tricky, right? So that's the bit where there's a bit of uncertainty about where they might need to move to mid-century. Where there's real uncertainty, I think, is in a downstream and in this availability of low carbon primary and the environmental burden of scrap. And that's a discussion, as I say, that's ongoing and will, if not need to be resolved, then we'll need some clarity on that, I think, before we can have entity level pathways specifically for mid and for downstream. So in 5.3 today, we talk about ASI endorsed methodologies where available, when available. We are looking to build those methodologies and then to endorse those, or the standards committee to endorse those, but that should not stop action in the meantime. I don't think it does need to stop action in the meantime because the big picture is quite clear.
Great, Chris. So another question here is, when we think about industrial decarbonisation, we tend to think on operational emissions. I think you've done a good job trying to paint that bigger picture. You've talked about, moving from an energy economy to a materials-based economy. And so this question's about how does ASI view the increase in emissions from the need for new construction, the mining of new raw materials and so on? To what extent are we making sure those kinds of project emissions are part of the net zero big picture? And I guess we can talk on the standards, but also this complexity of the big picture and these broader allocation questions as well.
Yeah. So maybe to start off is to say that the mining emissions are relatively low as part of the whole, but as the industry decarbonizes towards 2050, those less material emissions increase. When you're investing in a new project, and a smelting project, let's say, you're going to see it with an extremely long lifetime, up to 70 years, some of the European, North American facilities plus. So you're going to, and if everyone has to be at 0.5 on average by mid-century, you're going to have to building at the lowest emissions today. I will have to be a little bit careful with this, I guess, but it's to say that, with that existing cohort of production decarbonizing by mid-century, a fair proportion of that is going to be replacement capacity. I see a question on energy efficiency. The energy efficiency gets you about 10, maybe 15%, if that, I think. So this is not about creep. This is about a complete retooling of the sector. And so new projects do have to be added at the lowest carbon at any one time. And that means in decarbonized grids using novel technologies, or at least with the capacity to have those new technologies embedded. And so on a 1.5 degree, they're going to have to be low. I don't know what more to say about that, but that's a good, that's maybe something that we've not addressed in the standard, other than you need a 1.5 degree pathway. So you'd expect that a new facility coming on stream would need to have that pathway defined. One more thing maybe to say is on transport. So the flow of materials, that scope 3 is coming through in the transport materials, is also material, and we had a couple of 45 minutes on that a couple of months ago. So I encourage people to go and have a look at some of the projects underway on decarbonisation of transportation.
Great. Did you want to switch to Christoph's ones in the chat about, can we really switch from fossil, thermal energy? I think particularly for primary, perhaps more generally, but primary because of its challenges of the, the large scale and the continuity, that's required in smelters.
Yeah. So I'm not a technology person, right? But there was a conference recently which talked about the use of electricity for different thermal processes for kind of low temperature and high temperature. And certainly there are challenges with the high temperature compared to the low temperature. But I got to turn your question around, Christoph, and this is what the IEA stuff is like, and the downstream folks say, is it really possible to get rid of pre-consumer scrap from the process? Is it really possible to put in anodes and decarbonize 65 million or the 65 million tons of global primary capacity in the next 30 years, starting from a baseline of 0? Is it possible to completely change the way that we design vehicles and buildings in order to keep quality scrap loops coming out? It's not possible, it's required. I mean, that's what the 1.5 degree pathway demands. And so I guess I'm not gonna, it's kind of what we need to do. Technological challenges locally will require investment and R&D to develop those, because otherwise, really, the truth is, and maybe this is something we've not talked about today, but is a future one, it's about displacement of aluminium. So other products coming in to eat into aluminium's market share, or even to consume less. So consuming less would get us to a point much quicker than energy efficiency. Anyway.
Yes, it's hard to imagine a scenario where we can really decouple consumption from all of these questions. So perhaps that's a good point to start to wrap on. Chris, any other closing thoughts or things that you wanted to cover off on?
No, but maybe it's to say that we, with the release of the standard the performance standard and the chain of custody standard, our work hasn't stopped there. So you will see guidance updates. You will see us working on some of these methods, some of these gaps in methods that are required to be filled. And in order to do that kind of work, we need the input of our members and wider stakeholders as well. So I encourage everyone who's on the line today to get involved in those discussions because, like I say, it's a systemic issue. So it's not about just focusing on the primary or just focusing on scrap. It's seeing how all of those elements interact with each other and play a role in decarbonising the system as a whole. So we need those voices. We need to hear from recyclers. We need to hear from technologists. We need to hear from civil society, from Indigenous communities who are impacted potentially by decarbonisation projects. So get involved is really my final message.
That's excellent, and that we all have work to do. Well, huge thanks to you, Chris, and thanks to everyone who put questions forward. If you have other questions for us, feel free to send them through to our info@aluminiumstewardship.org. .org for us to consider those as well. And if you have requests for other 45 minutes on sessions in the future, we're happy to hear them. Dad has posted the link to where these get recorded, so you'll be able to follow up on this on other sessions there. We have another one at the end of the month with Audi presenting on their kind of procurement plans with ASI Aluminium, so we invite you to join us for that as well. Massive thanks again, Chris. Great job. And huge topic that we will be continuing, obviously, to work very hard on with all of our stakeholders. Thank you all. Take care.
Thanks, Fiona. Thanks, everyone.